Okay, and I think with this we can hand over to our first speaker, Gianluca De Fezza. Gianluca, I think will make you now speaker, and you can share your screen. You're live.
All right. Do you see my screen already?
Yes, we do.
All right, perfect. So good afternoon, ladies and gentlemen. Welcome to the presentation of Computational Fluid Dynamics Analysis and Optimization of a Multi-Element Airfoil for an Airborne Wind Energy System. My name is Gianluca De Fezza, and I'm a Master of Science student at the Eastern Switzerland University of Applied Sciences. Let me shortly introduce what's the presentation structure. I will start with introduction, where I describe the motivation of this project. Then I will go further and talk about the simulation setup, the pre-processing in specific. Then I will also talk about the simulation results, where the airfoil is analyzed. And then in part 4, we have the geometry optimization, where I talked about the optimization parameters and also the improvement overview. And in the end, we have the conclusion. So let's start with the introduction. The motivation of this master research project, or the motivation was a master research project in collaboration with the Swiss startup Skypool. Professor Dr. Sarah Barber was the supervisor of this project. The drone, which is visible here, exists of a double wing design to maximize lift with reduced wingspan. Additionally, each wing is made of a multi-element airfoil that is right here, that maximizes lift and minimizes drag for best flying condition efficiency. As you can see here, this is the whole profile of the airfoil. We have up here the separate airfoil the main airfoil. Down here we have the strut, and below them we have two flaps. We have the front and the rear flap. These 4 separate airfoils built the whole airfoil for this drone, and the red line here represents the chord length. In this work, the aerodynamic performance of this multi-element airfoil is analyzed using a steady-state 2D CFD simulation. Then the geometry is optimized to maximize the Lloyd's power ratio, also called LPR in this project. LPR is defined by lift coefficient cubed divided by drag coefficient squared. And according to Skypool, LPR is analog to the power output of the generator. Now I come to the simulation setup. As I said, the analysis was done by using a steady-state 2D simulation using the CFD code OpenFOAM. The mesh exists of 50,000 cells built by hexahedrons. The area around the airfoils was refined, and additionally, boundary layers were used to increase the accuracy at the wall regions. That gave a y plus value of around 30 with a Newton-Spalding wall function. And of course, before the simulations were carried out, a mesh dependency study was completed in order to get the most accurate meshes for the simulations. Some boundary and initial conditions. The initial velocity was 50 meters per second, and apart from other conditions, the turbulence model Spallet-Alamars was used because there were no significant differences in the results between the other turbulence models, and yeah, in the end, the one equation is comparatively more efficient. Now I come to the simulation results. I start with the variation of LPR with the angle of attack. An angle of attack range from 0 to 30 degrees, and a Reynolds number of 1 million was tested. It can be easily seen that the best range of LPR is in the range from 15 to 20 degrees. And for that, this range here had to be analyzed in more detail. We have done that, especially with streamlines and pressure distributions. On the left side here, you see the pressure distribution of each separate airfoil. And on the right-hand side, you see again the airfoil with the names on it and the streamlines. And of course, the chord length and the angle of attack. Here at the angle of attack, we really see that we had a lot of flow separation in the main and the strut. We also recognize that on the pressure distribution, although the flaps look more or less okay, but it isn't usable to work with such an angle of attack according to the pressure distribution. When we increase the angle of attack to 6 degrees, the flow separation disappeared, although we still recognize some issues in the pressure distribution for main and strut. Even further at 10 degrees, we see the same, although it's improving, but still not perfect for the pressure distribution. And here at the angle of 17 degrees, we see really nice pressure distribution on main and strut, and also a big or nice plot for the front flaps. But when we increase the angle of attack to 25 degrees on the streamlines, we recognize that some stalling is occurring, and also the strut pressure distribution is decreasing again. So with that, we come to the geometry optimization. As I showed you before, the angle of attack with 17 degrees was the best for that. And we continued with this angle of attack. So here you see the 5 optimization parameters that were used for the optimization part. Here you see again the whole airfoil with all the parameters on it. And I named it here the different numbers of each parameter, or the ranges of each parameter. So first of all, we scaled the flaps, each flap separately, from 60 to 240 degrees percent, and similar for the scaling of the strut, we scaled it from 20 to 140 degree percent. And in the third place, we explored the interaction between scaling and the strut, the scaling of the strut and the flaps, of course, together. And then we had some modification in the flaps angle, ranging from -10 degrees to +10 degrees. And we also modified the vertical distance to the main airfoil from 65% to 275%. So for the first, the next few slides look always a bit similar. We have up here, we have the highlighted airfoils that are optimized. And down here, we see always the graphs for the relative lift coefficient, relative drag coefficient, and the most interesting one, the Lloyd's power ratio. We have here on the x-axis, we have the front flap scaling. And on the y-axis, we have the rear flap scaling. And 100% means that this is the unchanged geometry. And so we recognized with the simulations that it is most beneficial when we increase the front flap scale to around 120%, and we change it, the rear flap, to more or less 102%. So we have an increase in LPR of around 5.3%. Next, we optimized only the scaling of the strut. We have seen here that it is beneficial when we decrease the scale to the minimum of 20%, and we could improve LPR here by almost 40%. Next, the interaction. We changed the front and the rear flap scale to the same, and the strut scaling as independently. And we see here that we can improve it by decreasing the strut scale and the rear flap scale, or rear and front flap scale, to the minimum right down in this corner. And we improved LPR here by over 40%. Then also an interesting story is this front flap and rear flap angle optimization. Initially, we are located here in the map, and when we increase the front flap angle to around 3 degrees, and when we increase the rear flap to 10 degrees, the whole geometry is getting a bit more rounded, and we could improve LPR by 13.7% right here. The last optimization was the vertical distance to the main, like here. And for that, we recognized that it is most beneficial when we increase the distance. So we move the strut airfoil further away from the whole airfoil system. And we recognized that LPR is somehow stagnating a little bit. It doesn't make any difference anymore below here. And but however, we only see that we improved LPR only 7.5%. So having said that, here's a short improvement overview. So we could see that the optimum of angle of attack lies between 15 and 20 degrees. We also recognized that we had some strong flow separation and stall occurrence at 0, 6, and 25 degrees. The improvement are also conclude here. We see that the dark line is the initial geometry, and the purple one is the optimized aspect or approach. We see here that the flap scale is only little improving by 5.3%. We have a big improvement in decreasing the strut scale by 39.1%. We have an even better improvement by combining the flap and strut scales. So when we decrease all the scales of them, we could improve LPR by 43.4%. The flaps angle also has a good impact of 13.7%. And the strut distance doesn't really improve much, only by 7.5% compared to the others. That is quite the lowest, next to the increased flap scales. So that leads me to the conclusion of this presentation. With this project, we could make the flight behavior and the effects of geometric changes more understandable. Skypool benefits from the reported results very good, and it helped them for further developments to increase the efficiency of their airborne wind energy system. We have seen that the strut should be as small as possible with proper consideration to the mechanical structure. When it is not needed for mechanical structure, maybe it's also beneficial to leave it away. So we have seen that also the position, removing or increasing the distance to the main is beneficial. The flaps should be adjusted to the optimal angles for further developments. And I'm convinced that by combining all these optimization approaches together, we might even raise the LPR to over 50% improvement. Further work includes automated optimization strategies that allows us to altering the parameters at the same time. We ensure with that no local maxima have been missed out, and these results should then integrated into the Skypool's mechanical system model. So with that, I'm at the end of my presentation. I thank you very much for your attention, and I'm ready to answer some questions now.